When you look at a world map, you'll notice that the Atlantic and Pacific Oceans come very close at one narrow point in Central America. This is the Isthmus of Panama. For centuries, this strip of land acted as a natural barrier between the two oceans. Ships traveling between them had only two practical options. They could sail around Cape Horn at the southern tip of South America, a journey thousands of kilometers longer, often through severe storms. Or they could unload cargo on one coast, transport it across land, and reload it onto another ship. Both options were slow, expensive, and risky. Naturally, the idea emerged. What if ships could cross directly through Panama? A canal through Panama would dramatically shorten maritime routes. For trade, this meant lower transportation costs, faster delivery times, and more efficient global supply chains. For military powers, it meant something equally important: the ability to move naval fleets quickly between oceans. In the 19th century, as global trade expanded and industrial economies grew, a shortcut between the Atlantic and Pacific was no longer just an ambitious idea. It became a strategic objective. The first serious attempt to build the canal began in 1881, led by a French company under Ferdinand de Lesseps, the same engineer associated with the Suez Canal. The success of Suez created confidence. However, Panama presented very different conditions. Unlike the flat desert terrain of Egypt, Panama is mountainous and covered in dense tropical jungle. Heavy rainfall caused frequent landslides. Rivers, especially the Chagres River, were unpredictable and prone to flooding. The French plan called for a sea-level canal, similar to Suez. But cutting through elevated terrain in a tropical climate proved far more difficult than expected. At the same time, yellow fever and malaria spread rapidly among workers. At the time, the role of mosquitoes in transmitting these diseases was not yet fully understood. The combination of engineering challenges, financial mismanagement, and high mortality led to the collapse of the French effort in 1889. The project was abandoned. After the French withdrawal, the idea of a canal through Panama did not disappear. At the beginning of the 20th century, the United States saw the project as strategically essential. For the U.S., this was not only about trade, it was about naval mobility and geopolitical influence. Moving warships between the Atlantic and Pacific quickly would significantly strengthen national defense. At that time, Panama was still part of Colombia. Negotiations between the United States and Colombia failed. In 1903, Panama declared independence. Shortly afterward, the new Panamanian government signed a treaty granting the United States the right to build and administer the canal within a designated canal zone. Construction officially began under American control in 1904. The Americans inherited not only the project, but also its problems. One major decision had to be reconsidered immediately: the type of canal. The French had attempted a sea-level canal, but Panama's terrain made that approach extremely difficult. There is a central ridge running across the isthmus. Heavy rainfall destabilizes soil and rock. Digging down to sea level would have required massive, continuous excavation with constant risk of landslides. American engineers adopted a different solution. Instead of cutting the land down to the ocean, they decided to lift the ships up. The new plan was a lock-based canal system. Ships would enter chambers, be raised approximately 26 meters above sea level to an artificial lake in the center of the isthmus, then lowered back down on the other side. This design dramatically reduced excavation and made better use of the natural landscape. Engineering was only one part of the challenge. The other was health. During the French attempt, yellow fever and malaria had caused thousands of deaths. By the early 1900s, scientific understanding had advanced. Researchers had confirmed that mosquitoes were responsible for transmitting both diseases. Under the leadership of U.S. Army physician William Gorgas, a large-scale sanitation campaign began. Swamps were drained, standing water was eliminated, buildings were screened, fumigation programs were implemented, strict public health measures were enforced. These actions significantly reduced disease rates. Without this medical and sanitary breakthrough, the canal could not have been completed. Health management became as important as excavation. Once the design was finalized and disease rates were reduced, the most demanding phase of construction began. The central obstacle was the Continental Divide, a chain of hills running across the isthmus. To create a navigable passage, engineers had to carve a massive trench through solid rock and unstable soil. This section became known as the Culebra Cut, later renamed the Gatun Cut. It stretched roughly 13 kilometers and required the removal of millions of cubic meters of material. Steam shovels operated daily. Explosives were used to fracture rock. And an extensive railway system carried debris away from the excavation site. The railway network became the logistical backbone of the project. Without it, continuous excavation would have been impossible. Despite improved planning, nature remained unpredictable. The region's geology presented serious challenges. Certain soil layers became unstable when exposed to air and water. Heavy tropical rains increased the risk of landslides. Excavated slopes frequently collapsed back into the cut. In some areas, workers had to remove the same material multiple times. These repeated setbacks slowed progress and increased costs. The challenge was not only digging deeper, but stabilizing what had already been dug. Over time, engineers adjusted slope angles and improved drainage systems to reduce further collapses. Even so, the Culebra Cut remained one of the most technically demanding aspects of the entire project. At its peak, tens of thousands of workers were employed on the canal. Laborers came from many countries, including the Caribbean, Europe, and the United States. The scale of the operation was unprecedented. More than 200 million cubic meters of earth and rock were eventually removed during the American phase alone. Entire hills were reshaped. Rail lines were constantly relocated to follow the progress of excavation. The canal was not a single construction site. It was a moving industrial system operating across the isthmus. By the early 1910s, the major structural components were taking shape. The excavation was advancing, the lock chambers were rising, and the artificial lake was beginning to form. The project was entering its final stage. Excavation alone was not enough to complete the canal. Water control was equally critical. The Chagres River, which runs through Panama, was one of the greatest natural challenges. During the rainy season, its water level could rise dramatically, flooding surrounding areas. Instead of trying to fight the river continuously, engineers chose a different solution. They built a massive dam at Gatun. The Gatun Dam created Lake Gatun, one of the largest artificial lakes in the world at the time. This lake became a central part of the canal itself. Ships would not only pass through excavated sections, they would navigate across this artificial lake for a significant portion of their journey. The project had transformed a natural obstacle into a functional advantage. The most distinctive feature of the Panama Canal is its lock system. Unlike a sea-level canal, the Panama Canal lifts ships approximately 26 meters above sea level to reach Lake Gatun. Process is based on gravity. When a ship enters a lock chamber, the gates close behind it. Water flows into the chamber through a system of large culverts and valves. As the chamber fills, the ship rises slowly and evenly. Once it reaches the level of the next section, the forward gates open, and the vessel moves into the next chamber. The same process works in reverse when ships descend toward the opposite ocean. No pumps are required. The entire system operates using gravity and carefully controlled water flow. In principle, it is simple. In scale, it is enormous. Precision inside the locks is essential. The chambers were built with minimal extra space relative to ship size. For much of the canal's history, electric locomotives, commonly called mules, guided ships through the locks using steel cables. These locomotives did not pull the ships forward. Instead, they kept them centered and prevented contact with the lock walls. Today, tugboats assist with positioning, but the requirement remains the same. Control must be exact. The canal is not simply a passage, it is a coordinated mechanical system where timing, alignment, and water levels must function together continuously. The Panama Canal officially opened on August 15, 1914. Its completion dramatically altered global shipping routes. Journeys between the east and west coasts of the Americas were shortened by thousands of kilometers. Trade between Asia and the Atlantic world became more direct. Ports, shipping companies, and global supply chains adjusted quickly to the new reality. The canal was no longer an engineering project. It had become a permanent part of the global economic system. From the beginning, the canal had a physical limit, the size of the ships it could accommodate. For decades, vessels were specifically designed to match the maximum dimensions of the original locks. These ships became known as Panamax, but global trade continued to grow. Container ships became longer, wider, and capable of carrying far greater cargo volumes. To remain competitive, the canal had to adapt. In 2016, a major expansion project was completed. New, larger lock chambers were added. These allowed the transit of significantly bigger vessels, commonly referred to as NeoPanamax ships. The expansion ensured that the canal would remain relevant in modern global trade. Despite its size and engineering sophistication, the canal depends on one critical resource: fresh water. Every time a ship passes through the locks, millions of liters of fresh water flow from Lake Gatun toward the sea. This water is not recycled in the original system. Instead, it relies on consistent rainfall to replenish the lake. In years of reduced rainfall, water levels drop. When that happens, the number of daily ship transits must sometimes be reduced. This makes the canal sensitive to climate patterns and long-term environmental change. In this way, even one of the world's greatest engineering systems remains dependent on natural conditions. For much of the 20th century, the canal was administered by the United States through the Panama Canal Zone. However, questions of sovereignty remained central in Panamanian politics. In 1977, treaties were signed establishing a gradual transfer of control. On December 31, 1999, full administration of the canal passed to Panama. Since then, the canal has been managed by the Panama Canal Authority and has become one of the country's primary economic pillars. Beyond economics, the canal remains strategically important. It influences shipping times, trade costs, and the movement of energy and goods between major global markets. Today, the canal operates as a highly coordinated system. Ships reserve transit slots in advance. Upon arrival, they are guided through a sequence of locks, raised to lake level, navigate across Gatun Lake, pass through the Culebra Cut, and descend through locks on the opposite side. The full passage takes several hours. For global shipping routes, it saves days. Each transit is carefully scheduled. Water levels are monitored continuously. Traffic flow is managed with precision. The canal functions as both infrastructure and strategic corridor. The Panama Canal began as a response to geography. A narrow strip of land stood between two oceans. Through engineering, planning, and decades of effort, that barrier became a passage. It required massive excavation, innovative design, medical breakthroughs, and political negotiation. More than a century after its opening, it remains one of the most important connectors in the global trade network. A reminder that infrastructure can reshape geography and influence the movement of the world.